All right, here we are in one more section that we're going to be reviewing before we end up getting into chapter 1, and that is just reviewing what an inverse function is and taking a look at what an inverse is. And then what we're going to do is determine whether that inverse is a function or not. So let's go ahead and review what is actually an inverse. An inverse, you are taking your x and y values and you are flip-flopping them. So your x is going to become your y and your y is going to become your x. You're just switching those around. So if you had a coordinate of, say, 7, 8, the inverse of that would be 8, 7. As far as thinking of equations, if you had the equation of y equals 5 times x, the inverse of that would be x is equal to y divided by 5. Really what you're doing with the equation is you're just solving for the other variable. So now let's take this concept of taking our coordinates here and switching those around, and let's take a look at some just basic functions. Here I have a linear function, so we're looking at y is equal to x, y-intercept is 0, slope of 1. Well, if I take points that are along that line right there, 1, 1, -3, -3, notice that if I flip-flop those, that they're going to stay the exact same thing, so that's not going to change. It's going to be the same graph. Understand that if I had a slope here of something other than 1, those coordinates would be different and it would not be the same graph. Quadratic function, if we look at that in our parabola here, taking the points of 1, 1 and 2, 4, I could plot those points of 1, 1 and 4, 2. Could also look at another point here. I could look at -2, +4, and looking at where that point is, and so that would be 4, -2. So seeing how that works out. Cubic function, again, plotting those points and flip-flopping them, and it takes that little curve right here and really just puts it onto its side. And the exponential function here, working with b being something that's greater than 1, that allows us to have the exponential growth. And then right over here on the other side here, that point would now become 1, 0 rather than 0, 1. Something else that happens with the exponential function is the fact that you have asymptotes, and your exponential growth has an asymptote along your x-axis. Well, the reciprocal, or not the reciprocal, sorry, the inverse of it is going to flop that around, and now you'll have a asymptote along your y-axis. So that's something kind of different. And then lastly, just looking at absolute value, taking a look at some of those points. This is very similar to the parabola and the fact that it's taking that v and turning it over onto its side. So if you can understand the concept that you're going to take a coordinate and you're going to flip the x and the y coordinate, it makes graphing things out fairly easy, because if you can find a few points, you can plot out those couple points, and there you have your graph. Now let's take a look at, are these inverses going to be functions or not? Obviously the functions that we started with, they all are, because they pass the vertical line test. And we know that in order to be a function, every independent variable, there's exactly one dependent variable. It must pass the vertical line test. So if I go back to some of these basic functions that we were looking at, just starting with the first two here, notice that first of all, the linear function, that passes the vertical line test. The quadratic function passes the vertical line test, which is good, because otherwise I wouldn't be able to call these functions. If I take the inverse of that linear function, it still passes the vertical line test. If I take the vertical line test of the inverse of the quadratic, we've got a little bit of an issue because it's passing through 2 points. So here we're looking at the inverse not being a function. Over on the other side here, we're going to take a look at the cubing function. That passes the vertical line test, and so does the inverse. And exponential growth, well, that passes the vertical line test as well as its inverse does. The absolute value is going to come into a problem just like the parabola did, in the fact that even though the absolute value is a function, its inverse is not a function. And this can be easily just done by testing out your vertical line test. Now you also have another option that you could do, and that is what's using called the horizontal line test. So to figure out if an inverse is a function, you can go ahead and apply the vertical line test to the inverse of the graph. Or rather than having to graph out the inverse, you can go ahead and look at the original function and apply what's called the horizontal line test. If I were to go back to some of these graphs right now, and this time if I was to do a horizontal line test to the original function, notice it passes here, and that means that the inverse is a function. If I do the horizontal line test here on the quadratic, it passes through twice, so the inverse is not a function. The cubing function passes through once, so the inverse is a function. Exponential growth, my horizontal line passes once, so the inverse is a function. Here, if I use my horizontal line test, it passes through twice, so the inverse is not a function. So what's the whole point of inverses? What are they going to do for us? Well, what it allows you to do is really solve an equation for something else. And you'd be amazed at how much we are doing this, especially when you are solving equations. When you have an equation of y equals 5x plus 2, and you plug something in for y, and you're solving for x, ultimately you're working with the inverse. When you talk about inverse, we're going to be looking at this new notation. Okay, it's using this superscript of -1. So this is saying that the inverse function of f of b is equal to a if and only if f of a is equal to b. Notice that, really your variables here are switching places. So you're taking f of b equals a, and that's only if f of a is equal to b. Two kind of good examples that we can look at here are, working with some formulas. Talking about the formula of going from degrees Fahrenheit to degrees Celsius. So 5/9 times f minus 32. Well, if you were to rewrite this equation and solve it in terms of degrees Celsius instead, that right there would be an example of an inverse. You're solving for the other value. This can be really helpful if you were trying to do a bunch of conversions, and rather than solving out the equation every time, you could use a different formula. Same thing goes down here in the bottom of working with the area of a circle. So the circle C of r is equal to pi r squared. That's our area. Well, if I wanted to go ahead and change this around, I could say that the inverse of this is the square root of area divided by pi. And that would then end up giving you your radius. So inverse functions can be really helpful. So let's just take a look at finding some inverses here algebraically of some basic equations. Starting out with f of x is equal to 6x minus 3. F of x is just a fancy way of saying y is equal to 6x minus 3. And when we solve our inverses, because we may end up plugging them into our calculators and having our calculators graph them out, we're going to always want to have our equations solved for y. So with finding an inverse, first of all, what we're going to do is we're going to switch these variables of x and y. So now it's going to be x is equal to 6y minus 3. I'm going to go ahead and I'm going to solve this equation now for y. So that if I had to, I would be able to go ahead and easily be able to graph this out on my calculator because it's equal to y. So I added 3 to both sides. I am dividing both sides by 6. And so I'm getting 1/6 x plus 1/2 is equal to y. This right here is the inverse. All I'm going to do right now is put back in the function notation. Since I'm talking about f of x, this is going to be the inverse function of f of x, which will equal 1/6 times x plus 1/2. So switching the variables, solve for your value of y, and then just rewriting the expression. Okay, taking a look at a different one here. So again, this is just the same thing as y is equal to x divided by x plus 1. So we're going to start out by switching the variables around. So x is equal to y divided by y plus 1. Now here you have to just be really careful because you have y's in two different places, so we're going to have to be a little creative of how we're going to get those together. Also the fact that you're working with a fraction here, what I'm going to go ahead and do is I'm going to get rid of this fraction by multiplying both sides of the equation by y plus 1. And so this is going to give me y plus 1, the quantity of that, times x is equal to y. Now, ultimately here again, we need to try and get our y values together. And I'm going to need to get rid of this parenthesis somehow, so I'm going to go ahead and distribute. So y plus, or sorry, yx, almost missed that part, so it's y times x. So y times x plus x then is equal to y. Figuring out, okay, y's, I've got to get those on the same side, so I'm going to go ahead and subtract a yx from both sides. Now, this type of solving, you probably have not done a whole lot of it, so this might be something that you might have to practice a few times. But I'm still got these two variables, so that's what's kind of taking us for a loop. But at least now I have the y's on the same side. And what I can do at this point is I can factor out a y, and I'm left with 1 minus x. And so now if I have y times 1 minus x is equal to x, we can go ahead and divide both sides of this equation by that factor of 1 minus x. And we end up with y by itself. And so y is equal to x divided by 1 minus x. Our inverse function of f of x is equal to x divided by 1 minus x. And there would be the inverse of this. So now with this whole idea, let me take you back to some of those basic parent functions that we were looking at, and let's take a look at what some of those inverses are. As far as your parent or your basic function of the linear one here, well, if this is y equals x, it's the same thing. So those two graphs are identical to each other. But how about this one? Y is equal to x squared. So now x is equal to y squared. Well, think about it. How do we solve for y in this case then? We would take the square root of both sides. And so then this would end up giving me that y is equal to the square root of x. Now, we talked about how the quadratic function, the inverse, is not a function. Okay, so we talked about how it doesn't pass that vertical line test. It also doesn't pass that horizontal line test. Well, when we look at this here, we actually change something about this function so that it does end up being a function for us. Because the inverse of the quadratic function here is f of x is equal to the square root of x. That's how you solve for x in this situation. Well, the thing is that when you take the square root of something, we cannot take the square root of negative numbers. And so what we do in this case here is we talk about restricting the domain. When you're looking for an inverse of a function, what we're going to do is we're going to ignore part of your original domain, which your original domain of your quadratic is all real numbers. Well, if we were to find the inverse of this, we are going to eliminate those negative values, which then gets rid of them here. And this right here then ends up being our square root function. If I were to get rid of this bottom half, well, now that graph passes the vertical line test. And so right here, the inverse function of f of x would equal the square root of x. If you were to take a look at the cubing function, okay, so you've got y is equal to x to the third. We looked at x is equal to y to the third. Recalling that to get rid of a cubed root, or a cube, sorry, we would take the cubed root of both sides. So our inverse function here is going to be the cubed root of x. And we'll get into this graph when we start talking about our polynomials and powers. But this is also known as x to the power of 1/3. So there's our inverse there. When you talk about exponential ones, so y is equal to b to the power of x. Here's where, in order to solve for x, if this is x equals b to the power of y, you may recall that we would have to take the log of both sides because you've got to get that exponent down. And so here, this function right here, the inverse function of your exponential is going to be the log base b of x. So now hopefully you can see how these are working together. Now the one thing here is that the absolute value does not have an inverse. We do not do anything with restricting the domain like we do with the quadratic one for this. All right, so lastly what I want to do is talk about how can you verify that two functions are inverses of each other. Well, we've already talked about how to do a composition of two functions, and that's exactly how we can verify that two functions are inverses of each other, more so going for the algebraic approach to it. So what we can do here is if you can do the composition of f of g of x is equal, and it equals x, or vice versa, g of f of x equals x, then what you have here is you have two inverses that are reflections of each other, and therefore that they are inverses of one another. So I have an example here of f of x and g of x. Well, if I go ahead here and I want to evaluate f of g of x, so I'm going to go ahead and g of x is equal to the cubed root of x minus 1. So now I'm going to take the function f of x, and I'm going to take my cubed root of x minus 1, and I'm going to plug it in for x. So this is going to end up giving me the cubed root of x minus 1 to the third power plus 1. Well, a cubed root and a third power cancel each other out, leaving us with x minus 1 plus 1. Negative 1 plus 1 ends up giving us 0, so we end up with x. This right here is a verification that these two functions are absolutely inverses of each other. Now, yes, you could go ahead and you could solve this and show it that way. This is just a way of using compositions. You could also do this the other way of g of f of x. And one thing that you're going to understand, that especially in pre-calc here, is that there's not always one way to do things. And what I want you to be able to do here is you've got to keep an open mind about looking for ways of proving things in different ways, because sometimes when you get into later at mathematics, is sometimes the one thing doesn't always work, and so you've got to be looking at multiple ways to attack a situation. If I did the other composition here, so g of f of x, this time I would take x to the third plus 1, and I would be plugging it in for x in the function of g. And so this is going to end up giving me the cubed root of x to the third plus 1 minus 1. Well, plus 1 minus 1 is 0, so I'm going to get the cubed root of x to the third, and that right there simplifies as x. All right, so before I get too long-winded in this video, I'm going to go ahead and stop there. Hopefully you can recall the inverses, and possibly verifying the inverses, possibly a new piece of information for you. As always, if you have questions, make sure that you are jotting them down.